Hello everyone, Rashid here. Thank you so much for joining. And today's video is about the new playlist or series that I'm starting, and that is on timing constraints. So this will be a quick intro of the timing constraints series, as well as just some high level picture where we are and what is coming. Okay, so yeah, so if it is the best if you really want to look into this. This is a track 2 in my training series in the training videos. Okay, I have a track 1 which is a foundational course, and I talk about that in a previous video on the last video of the RISC-V architecture. And this is the track 2, which is physical design and STA deep dives, where I go deeper into topics of physical design. So this is for those folks who are already in physical design. And by the way, this information is available on this website. So if you go there, you will see this. And these are the links. So since I have a lot of videos, I thought it'd be easier if I sum it up on the website and then have the links for the individual playlist. So if this is the first time you're looking into it, then I think what you should here let me give you the sequence, right? Sequence. Okay, so this one, the physical design flow. Here I took a block from all the way from synthesis, an RTL block, small, and from synthesis all the way to route. And I actually gave the commands of the tools to demonstrate the flow. And at each stage of the flow, I provided concepts. What is placer doing? What is router doing? What is happening in CTS? And even some of the fundamental steps, how you can create a layout database, how you create a library, how to create a cell. Within synthesis, we look in pretty much detail on different steps. So if you want to start on physical design, and especially on taking a block through RTL to GDS flow, then this is the best place. After that, I think within there, I even touch on clocks, and this, so I put some of these clock trees, sorry, not on the class, clock trees, clock tree and global and local clock trees. So I even created them into a separate playlist. So within this, I will give a reference of global and local clock tree, but you can also watch this separately just to give you some high level concepts. This one, and after this, I think the best is that you come to the block level timing flow. So we did a lot of videos on this, the block main timing concepts as well as the block level timing flow. I did do a couple of videos, I feel, on the full chip side, but a lot of methodology stuff in different areas I covered there. And after that, I did a series where I took questions. Where is that thing? Oh yes. Oh yeah, I had this one. Okay. So I think, I don't know how many videos I created, but after this, you should also look into this one. And then there was a high demand for a full chip timing series, so I started this. So in the first part, I covered the flow side, all the way from starting libraries. Then especially I focus a lot on the creating scenarios or views. Okay. And after that, the next topic is the timing constraints. So the timing constraint part, I think even on the track 1 in physical design, I covered some timing constraints. Then during this, we also look into timing constraints. And yeah, I think that's it. So initially I created this playlist with the videos from, I believe, this one and the other track 1 physical design. But right now, when I was creating timing constraint, I really wanted to look into full chip. Okay, block level, you have some idea, and then go to the full chip. What will be the different things that you need to keep in mind as a full chip timing person? But then there were requests on the basics of those. So here is what I'm thinking right now. I'm thinking that, okay, I create this playlist or series where I go through all the timing constraints. By the way, when I say timing constraints, these are the subparts of that. So you have clock definitions, you have IO constraints, you have exceptions, and you can have some special checks or asynchronous path up checks. Okay, so these typically are the four things that comes to my mind when somebody talks about timing constraints. And then we need to talk about those at a block level full chip. Your full chip can be a subsystem, which is a lot of blocks in a subsystems, and then a lot of subsystems and blocks can be in the top level or die level. Okay, at Intel we used to have even subsystem and then sub full chip and then full chip, but these I combine kind of block, subsystem, and then top down. Yeah, full chip top. This is becoming a new full chip, 3D IC level, and becoming gradually popular now. A lot of companies moving towards that. So, but full chip flows means okay, it's the next level hierarchy after block. And if you understand concept of subsystem, the concepts here might not be that much different. There are some unique concepts applied here, and we will talk about those too. But I think my goal is that when I cover these topics, I talk first at block and then full chip. So, for example, when I start clock definitions, right, and in the one clock definition, and then when you have generator clock definitions, then you can have slow to fast, fast to slow type of. Actually, that comes into exception, but those clock definition we can look into from block level, from full chip, and then I/O constraints. I/O constraint at partition level or block level, you need to constrain your input output ports, right? So that one, and then you also, when you're at full chip level, you need to generate I/O constraints for your block level. That's called a budgeting. So you need to consider that one. And then at the same time, when you roll up, some in some hierarchical flow, there also you generate contexts as well as SDCs, right? And the blocks execute those and can generate a flat roll up to the top as well as can generate a hyperscaler boundary model. We will look into those. Maybe under hierarchical, but I/O constraints definitely play a good role there. Then at full chip, you also have pads. Those we call them ACIOs, right? How you need to constrain those because those signals are leaving the chip or they are coming from outside the chip. So you need to constrain those as well. So that's another part there. And then when you come into exception, you have false path. You can have multi-cycle paths, and this is where I was talking about slow to fast, fast to slow, right? And then async clock groups. What are those? And here sometimes gray coding, sometimes things come between a different clock coming from different PLLs. Typically, it's called a clock domain crossing. Okay, when clock domain crossing happens, you need to synchronize them, and sometimes your usual checks are not applicable there because those are two separate clocks. You need to maybe ensure that your skew within the data bus is good, or skew between clock and data is good, right? Some of those things you need to look into. So I will look into giving you some scenarios where we can look into those. So goal is we look all of this from both block and full chip point of view. That's one message I want to give you. The other one is, I think in this one it's important that for complete everything, I start from basic level and go to the advanced level. So it might be a little boring for those people who are already advanced, and I do see some people who follow me on this timing series. They have good experience, so it might be a little boring for them, but bear with me. I think it's still better to start from basic all the way to the top. So if next time somebody asks me questions, okay, then I can refer them to, hey, go to this playlist and start from A to Z. Okay, makes sense? So yeah, I think that's all I wanted to do. So I will start with clock definitions from next time. Okay, that's all for now, and I will see you pretty soon in the next video.